In this video, I will be discussing about the shortcut of doing integration by parts repeatedly. Actually, there are instances that we apply integration by parts more than once for a particular integrand. And doing that integration by parts repeatedly for a particular integrand, say twice or thrice or more, could be a cumbersome process. In situations like this, there is a way to organize the calculations that shortens the length of work of doing this integration by parts repeatedly. And this is called a tabular integration, which is now popularly known as the DI method. So what is this DI method? To illustrate, let's have our example number 1 here. What is the integral of x squared times e to the x dx? Actually, I have done this example in our previous video, in the video of doing integration by parts the usual way, and we applied here integration by parts more than once because looking at the integrand, it is a product of two different functions. This x squared, which is an algebraic function, and this e to the x, which is an exponential function. So how do we do this tabular integration? First, let us have the D column here, and we have also the I column here. D stands for derivatives and I stands for integrals. So we will write our U in the integration by parts under the D column. So our U is x squared here, and our dv is e to the x. So what are we going to do is to apply differentiation to this x squared repeatedly. So what is the derivative of x squared? The derivative of x squared is 2x. And what is the derivative of 2x? The derivative is 2. And what is the derivative of 2? The derivative of 2 is 0, because 2 is a constant already. And in the I column, we don't differentiate there, but we integrate e to the x. So what is the integral of e to the x? The integral is e to the x. And then we need to apply for the second time the integral of e to the x. And the integral of e to the x is still e to the x. And again, what is the integral of e to the x? Is still e to the x here. So we are applying integration repeatedly for this e to the x. And we stop at this time because we obtain a 0 in the D column. So we stop because we have a 0 in the D column. And then we multiply the first term here by the second term in the I. So here we multiply there, and so with this, and so with this one. But the signs here are alternating. This is positive, negative, positive, and so on. So to obtain the answer of our required integral, which is the integral of x squared times e to the x dx, it is equal to this x squared times e to the x. So we have x squared times e to the x. And then we multiply this negative 2x to e to the x. So we have minus 2x times e to the x. And then we multiply next 2 to e to the x. So we have plus 2 times e to the x. And this will be added to the constant of integration c. So this is now our answer for this example. And you can check that I have the same answer with my answer in the previous video when I was doing the usual way of doing integration by parts repeatedly for this particular integral. So as you can see, this is a DI method because you have two columns here. The D column for the differentiation column and the I column for the integration column. So I was doing differentiation repeatedly and integration repeatedly here. And then I stop when I get a 0 in the D column. But don't forget that the signs are alternating here. So positive, negative, positive there. Now let's proceed to the next example. What is the integral of x squared times sine 2x dx? Actually, I have done this example in our previous video using the usual way of doing integration by parts. In that video, if you have seen that video, I used this x squared as my u and this sine 2x as my dv. So here I will be doing the DI method. So this is my differentiation column and I have also the integration column. So I will write here my u, which is x squared, and my dv as the sine 2x here. And then I will apply differentiation repeatedly here. So the derivative of x squared is 2x, and then the derivative of 2x is 2, and also the derivative of 2 is 0. And then I stop because I get a 0 in the D column. But I need also to get the integral of sine 2x. And the integral of this is negative 1/2 cosine 2x. Why? Because when you integrate sine 2x, you need to have a 2 because by chain rule, you need to get the derivative of 2x, and the derivative of 2x is 2. But actually, I don't have a 2 here, so to have a balance, I need to multiply 1/2 here. And we know that the integral of sine is negative cosine. So that's why we have negative cosine 2x. And what is the integral of negative 1/2 cosine 2x? That is negative 1/4 sine 2x. And how do we get that integral? We integrate negative 1/2 of cosine 2x. But we need to have a 2 as the derivative of 2x. But actually I don't have a 2 here. That's why I need to have a balance of multiplying 1/2. And we know that the integral of cosine is sine. That's why I have here negative 1/4 sine 2x. And what is the integral again of negative 1/4 sine 2x? The integral is 1/8 of cosine 2x. Because obtaining the integral of negative 1/4 sine 2x, I need to have a 2 as the derivative of 2x here. And to have a balance, I need to multiply here to neutralize a 1/2 in front of the integral symbol. That's why this is 1/8. But this becomes a positive 1/8 because we know that the integral of sine is negative cosine. So negative cosine times negative 1/8 is positive 1/8 cosine 2x. But we stop here our iteration because we have a 0 in the D column. So to get the answer for the integral of x squared sine 2x dx, we have this one here, multiplying x squared to this negative 1/2 cosine 2x, but positive. So this is negative 1/2 x squared cosine 2x. And then multiply next this one, but with the minus sign. So negative 2x times negative 1/4 sine 2x is positive 1/2 x sine 2x, because negative 2x times negative 1/4 is positive 1/2 x, and then multiply this one here, but this is a positive 2, so we have positive 1/4 cosine 2x, and this will be added to the constant of integration c, and this is our answer for this example here. So as you can see from these two examples, we stop the iteration of doing differentiation and integration when you obtain a 0 in the D column. Actually, there are 3 cases when to stop the iteration. This is only the first case that we stop when we obtain a 0 in the D column. I will present to you the second case here in example 3. So here in this example, what is the integral of e to the 2x times cosine 3x dx? In the previous video, I was able to solve this one using integration by parts, but using the usual way of doing integration by parts, and it was very long process. This time we will be doing the shortcut method called the tabular integration or the DI method. So I will be writing here the D column and the I column here. So for the D column, I will be writing our u, which is e to the 2x here, and in the I column, I will be writing cosine 3x. So taking the derivative of e to the 2x, we have 2e to the power 2x, because by the chain rule, I need to get the derivative of 2x, which is 2. And then taking the derivative for the second time of this one, we have 4e to the 2x, because the derivative of e to the 2x is 2e to the 2x, but I have a 2 here already, so 2 times 2 is 4. While in the I column, I need to find the integral of cosine 3x, and the integral of cosine 3x is 1/3 sine 3x. Why? Because when I solve the integral of cosine 3x, I need to have a 3 as the derivative of 3x in the integrand. But to neutralize this 3 here, I need to multiply 1/3 in front of the integral symbol, so that 1/3 times 3 is just 1. And we know that the integral of cosine is positive sine. So that's why this is 1/3 sine 3x. And then finding the integral again for this one, we have negative 1/9 of cosine 3x, because finding the integral of 1/3 of sine 3x, I need to have 3 in the integrand as the derivative of 3x. But to neutralize the 3 which I added there, I need to multiply 1/3 in front of the integral symbol. So this 1/3 and this 1/3 is equal to 1/9. But this is negative because the integral of a sine is negative cosine. That's why the answer is negative 1/9 of cosine 3x. And I stop here, although I have not seen a 0 in the D column. Why? Because I see e to the 2x and cosine 3x here, which is the same in the first row here. So I stop. So we write here, we stop since a row repeats here. In other words, we see a row that is the same with the first row, although we have a different constants here, but the same functions. E to the 2x, e to the 2x, cosine 3x, cosine 3x. So we stop there. So this is a second case that even if we have not seen a 0 in the D column, but we see the same functions as in the first row, then we stop. So we multiply this one and also this one here, but the signs are alternating. So we write that the integral of e to the 2x cosine 3x is equal to this e to the 2x times 1/3. So we have 1/3 times e to the 2x sine 3x. And then multiplying this negative 2e to the 2x times negative 1/9 of cosine 3x, we have positive 2/9 e to the 2x times cosine 3x. And then we need to multiply the last row here. Now, why is it that we don't multiply in the last row? Actually, we need to multiply this one here. But since one of its multiplier is 0, then there's no need to multiply. So multiplying 4 to negative 1/9 is negative 4/9 times the remaining row. So this is negative 4/9 of the integral of e to the 2x cosine 3x dx. And where did I get this one? This is just the product of this e to the 2x and cosine 3x here. And also I need to multiply 4 and the negative 1/9, which I place here in front of the integral symbol. And looking at this equation, I realize that this integrand is just the same with my given integrand. So what will I do is to add both sides of the equation by the positive of this expression, so that this expression at the right will be removed. So adding 4/9 times the integral of e to the 2x times cosine 3x dx at the right hand side of the equation, I need also to add 4/9 of the integral of e to the 2x cosine 3x dx here. So actually, I am adding same terms to both sides of the equation. So this term cancels with this one, but this one will be added to the given integral, which is understood to have a coefficient of 1. And 1 plus 4/9, by simple arithmetic, that is equal to 13/9. So 13/9 of the integral of e to the 2x cosine 3x dx, which is equal to 1/3 this one times e to the 2x sine 3x, and this will be added to 2/9 of e to the 2x times cosine 3x, and this will be added to the constant of integration c. However, we need to remove this 13/9, and to remove this 13/9, we need to multiply both sides of the equation by 9/13. So 9/13 times 13/9 is 1. So 1 times the integral of e to the 2x times cosine 3x dx is equal to 1/3 times this 9/13. And this will be multiplied to e to the 2x times sine 3x. And also the 2/9 will be multiplied to this 9/13. And this will be multiplied by e to the 2x times cosine 3x. And of course, this 9/13, which is a constant, when multiplied to another constant, is still a constant. So I will write here the big C. So our final answer, the integral of e to the 2x cosine 3x dx is equal to 3 over 13 times e to the 2x sine 3x, because one of the 3 in this 9 with the 3 in the denominator here will be cancelled to each other. And then we have 2 over 13 times e to the 2x cosine 3x, because the 9 here and the 9 in the denominator will be cancelled to each other. So what remains is 2 over 13. And this will be added to the constant of integration c. And this is now our answer for this example here. And you can check with my answer in the previous video when I was doing this one using integration by parts through the usual way of doing integration by parts repeatedly. So here I summarize the 3 cases when to stop the iteration in the tabular integration. We stop when we obtain a 0 in the D column. That is the first case. And we stop when a row repeats the first row, which I have illustrated through example 3 in our first board. And then the third case is we stop when we can integrate already the product in a particular row. So to illustrate, I will be solving this one, which is the integral of x cubed e to the power x squared dx. And actually, I have solved this example in our previous video. So if you have not seen that video, I will advise you to watch that video of integration by parts using the usual way of doing it. Now in that video, I use my u as the x squared and e to the x squared times x dx as my dv there, because it's very hard to integrate when there is no x here. Because in integration, we need to have the derivative of x squared, which involves x. So I need to have an x, which I borrowed from x cubed. So my u here is x squared, not the x cubed. So in my D column, I need to write x squared. And in my integral column, I need to write e to the power x squared x. So I need to differentiate x squared, which is 2x here, and then integrate also this one, which is 1/2 e to the power x squared. And to show that this is the integral of this is to write that the integral of e to the power x squared 2x dx. Actually, I don't have a 2, but I need a 2 here because the derivative of x squared is 2x. And where did I get 2? I added 2 there because I also multiplied 1/2 in front of the integral. So that 1/2 times 2, that is already 1, which is equivalent to the given integrand. So the integral of this is this one. And at this point, I need to stop. Why? Because I can already integrate this row here. Because this one is already like this. So I stop when we can integrate the product in the row. Because I can already integrate this product here. And that is the third case that we stop when we can integrate the product in the row. But take note, I need to multiply this one here by, this is a positive sign and this is a minus sign. So the answer is the integral of x cubed times e to the power x squared dx is equal to x squared times this, which is 1/2 x squared times e to the power x squared. And this will be subtracted by 1/2 of the integral of e to the power x squared times 2x dx. And where did I get this one? This is just the product of this. But I place 1/2 in front of the integral and the 2 here because I need the 2x as the derivative of x squared. And why do I need to stop? Because I can already integrate this one. So our answer of the integral of x cubed e to the power x squared dx is equal to 1/2 of x squared times e to the power x squared minus 1/2 of e to the power x squared plus c, because the integral of e to the power x squared times its derivative here is e to the power x squared. And you can check that this is my answer for this given integral in our previous video. And this is an example that illustrates the case number 3 that we need to stop when we can already integrate the product in a row. Also, I need to solve this example which I have solved in our previous video as an example 5 there. And in that video, I use ln x quantity squared as my u and this x squared dx as my dv there. So in my di columns, I need to write the square of ln x here in the d column, and x squared is in my I column. So finding the derivative of this, we have 2 ln x by the power rule, and by the chain rule, I need to multiply this one by the derivative of ln x, which is 1 over x, while the integral of x squared is x cubed over 3 here. But as you can see that when I multiply this row, I can simplify some variables there because this x in this denominator can be cancelled by one of the x in this x cubed. So rewriting this one as 2 ln x and this one as x squared over 3. So instead using this one, I will be using this simplified form of this. So taking the derivative of this, we have 2 times 1 over x, because we know that the derivative of ln x is 1 over x, while the integral of this one is x cubed over 9, because the integral of x squared is x cubed over 3, but we already have a 3 here, so 3 times 3 is 9. And then again, I can simplify this x in this denominator to one of the x here. So I have 2, and this becomes x squared over 9 when I cancel this x with one of the x in the x cube. So taking the derivative of 2, we have 0, and the integral of x squared over 9 is x cubed over 27, because the integral of x squared is x cubed over 3, but we already have 9 here, so 9 times 3 is 27. So actually I have 4 rows here, this row and this row, because the black one is just the reduced form of the first one, and also this one is another row, and this one is my 4th row. So actually I have 4 rows here. So multiplying this one with this one here, but also multiply this one here and this one here. So this is positive, negative, positive there, and then we stop because we obtain a 0 in the D column here. So my answer for this integral is the product of this one here, which is 1/3 of x cubed times the square of ln x. And this will be subtracted by 2/9 x cubed times ln x. So here, and this will be added to 2/27 of x cubed, and this will be added to the constant of integration c. Hence, this is my answer for this example 5 here. And you can check that that is my answer in the previous video when I was doing this example using integration by parts the usual way. So to recap, we have 3 cases when to stop our tabular integration here. We stop when we obtain a 0 in the D column. We stop when we see a row that repeats the first row. And we stop also when we can already integrate the product in a given row. So those are 3 cases, 3 possibilities when to stop our tabular integration as a way of organizing the integration by parts when applied repeatedly for a particular integrand. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.